So the next thing we're going to look at is distance from a point to a line and from a point to a plane. So here we have our line. It's ax plus by plus c equals 0. And we have this point P. And if you were doing an actual example, P, the x and the y would be actual values. And we want to find the shortest distance from this point to this line. And if you remember from grade 10, the shortest distance is always the distance that cuts the line at a 90-degree angle. It's always the perpendicular distance. So we want to find the length of this little red section right here. Because it's perpendicular to our line, we know that a vector that goes in the exact same direction as this would be the normal, right? Because a normal would also be perpendicular to our line. So if we want to find this length of this red section, what we actually are going to end up doing is we're going to take the vector QP, where Q is just some point on the line, so vector QP, which we can actually find by doing P minus Q, which is what they've done right here. There's our vector QP. And we are going to project QP onto N. And because we only want length, we're going to do the scalar projection of QP onto N. And that's exactly what this notation right up here means. So it's the component, you're taking the scalar projection of vector QP onto N. And if you haven't seen that notation before, that's just what it means. And because we care about distance, we don't want negative or positive, so we're just going to take an absolute value of it. Okay, so now we're going to go along and use our scalar projection formula. So remember, scalar projection says vector QP dot vector N all over the magnitude of N. Okay, so they do the dot product by multiplying the x components and the y components and adding them together, and that's how we get this next line. Okay, and then on the bottom, we've done the magnitude of vector AB, so that's just the square root of a squared plus b squared. Then to go to the next line, all they've done is they've taken ax and by and they've moved it to the front. And then they've grouped together all of these other numbers. Okay, and everything there would be a number, because a is a constant, x naught would be a constant, negative b would be a constant, and y naught would also be a constant. So all those numbers would combine. And if you remember back to the lesson where we talked about the Cartesian equation, that actually is what our constant c was in the Cartesian equation. So our distance has simplified down to the absolute value of ax plus by plus c all over the square root of a squared plus b squared. And that is how you find the distance from a point to a line in R2. And of course the x and y in there, that comes from our point. We would have plugged it in for x and y. So let's give this a try right now. So here's an example. We're finding the distance from the point 5, 2 to this line. So we're going to use that distance formula, which is really just the scalar projection simplified. So we're going to use our line, but we're going to fill the point in for x and y. So there's the line, and then it's all over the magnitude of the normal. So the a and the b, so we do square root of 3 squared plus negative 7 squared. And we simplify this, we get the absolute value of negative 18 over root 58, which means our distance is 18 over root 58. So there's our distance from that point to that line. Next, we're going to look at the distance from a point to a line in R3. So this one's different because, of course, the line doesn't have a Cartesian form. Okay. There's no one distinct normal for lines in 3 dimensions, so we can't just project PQ onto the normal. So we need to find the same distance here. We need to find FP. Still the perpendicular distance, because perpendicular distance is always going to be the shortest. So what we're actually going to start by doing is we're going to relate this angle here, so the angle between our line and PQ, and we're going to relate the length of this distance, so the magnitude of PF. And the way we do that is using SOHCAHTOA. So sine of this angle is going to be the opposite, which is the magnitude of PF, over hypotenuse, and the hypotenuse here is the magnitude of PQ. So that's how we got this equation right here. Okay, and it's just relating some stuff that we can find to what we need to find. So we need to find the magnitude of PF. That's what we're looking for. We'll be able to find the magnitude of PQ, and we would be able to find the angle between the two vectors if we needed to. It would just be a bit of a pain. Okay, so the first thing I'm going to do is I'm going to actually isolate for the magnitude of PF, because that's what we're interested in. Okay, and we would do that by just multiplying the other side by the magnitude of PQ. Okay, and we get the magnitude of PF is the magnitude of PQ times the sine of the angle. So that's what we've done so far here down in the distance section. So the distance is equal to the magnitude of PF, which we've already proven is actually just really that. Now, what the person who came up with this next thought is, I have a magnitude times sine of a theta. What does that kind of look like? Well, it looks kind of like the cross product formula, except that we're missing one component. So if we were going to find the cross product between vector PQ and another vector, that other vector would be m, because m is the direction vector of our line. And if we think about why we're dealing with cross product, it kind of makes sense, because cross product gets you a perpendicular vector, right? And distance, it's perpendicular to the line. So what they've done next is they've multiplied by the magnitude of vector m over the magnitude of vector m, which they're allowed to do because it's like multiplying by 1. And now this entire numerator is really just the magnitude of the cross product. So it's the magnitude of PQ cross m all over the magnitude of m. And that is how we find distance for a line in 3 dimensions. So let's give an example a try. So here we're finding the distance between this point, P, and this line. So they give us a point on the line, and they give us the direction vector. Now remember, we need a P, a Q, and an M. So the P we already know. The Q is a point on the line, which they've given us 1, although you could use any point if you really, really wanted to. And M is the direction vector, which they have also given us. Okay. And to find the distance, we are going to find the magnitude of PQ cross M all over the magnitude of M. Okay, so first we need to find vector PQ. And we can do that by doing Q minus P. So 3 minus 1 would be 2, 5 minus 4 would be 1, and 1 minus negative 2 would be 3. So there's vector PQ. And now we need to figure out PQ cross M. So that's when you do your little cross product memory trick. Okay, so give this a try and unpause the video to get an answer. Okay, so when you do the cross product, so multiplying the diagonal minus the multiplication of the off diagonal, you get 9, 3, negative 7. So going back to our distance formula, we're going to have to find the magnitude of 9, 3, negative 7 all over the magnitude of our direction vector, 5, negative 1, 6. Okay. So that's just really doing square root of 9 squared plus 3 squared plus negative 7 squared all over the square root of 5 squared plus negative 1 squared plus 6 squared. And if we work this all out, we would get the square root of 139 over the square root of 62, which ends up just being the square root of 139 over 62. Okay, and there's our distance. So next we're going to find a distance from a point to a plane. So here we're finding the distance from point P to this plane right here. Okay, so point Q, that is a point on the plane, and we would have a vector PQ going from the point to the plane. Now, because there is a specific normal for a plane, and we do have a nice Cartesian form, we can actually find the distance here the same way that we did when we were working with 2 dimensions, meaning we can project PQ onto N. And once again, because we only want the length, we're going to do a scalar projection. And I'm going to put it in absolute values because I want it to be positive. So I'm going to do the scalar projection of PQ onto vector N. So just like before, that would be PQ dot N all over the magnitude of N. Okay, so we do the dot product. When we dot this out, we would get this right here. Okay, so that is what we get from the dot product. And just like before, the AX, the BY, the CZ, those would all be pulled out front. And the rest of these constants, there should be a little knot there, would be combined and they would form another constant which we call D. We're going to find the absolute value of AX plus BY plus CZ plus D, okay, where X, Y, and Z is just the point that we're trying to find the distance from, so in this case point P. And it would be all over the magnitude of vector N. So let's give an example a try. So, just like before, we're doing the absolute value. We're going to take our Cartesian form here and we're going to sub in point P for X, Y, and Z. It's all over the magnitude of the normal, and the normal is 4, 2, 1. And if we work that out, we get 22 over square root of 21. And it's already positive, so the absolute values really weren't even needed. The distance would be 22 over 21. Okay, and there it is. So lines in 2 dimensions and planes are really just scalar projections. When we do the 3-dimensional one, we had to manipulate it a little bit to turn it into a cross product. So there is how we find distance from lines to points and planes to points. So you guys can get started on the homework and have a great week.